Good morning everybody. I am Dr. U.K.Khan and today I am going to give you a demonstration on the experiment to determine the refractive index of a liquid by total internal reflection using Wollaston's air film. Before going into the details of the experiment, let me first tell you what is Wollaston's air film and how it is prepared. This is the Wollaston's air film. We take two pieces of glass plates and we make some depression over here or some groove over here, and then we make them join with the help of good quality glue such that air inside gets trapped and we get an air film inside this envelope of glass medium. This is called Wollaston's air film. So we have air inside, air is trapped here, and we have the glass enclosure. So this is the Wollaston's air film. Now I come to the basic principle of this experiment. Suppose we have multiple layer of mediums of different refractive index. Like this, we have liquid, we have glass, we have air, again we have glass, and then we have the same liquid we started with. And if we make the light incident on this interface of glass and liquid, then there will be a refraction. Now again, at this point, on the interface of air and glass, there will be another refraction. And at this point, at the interface of glass and air, there will be another refraction. And at this point, at the interface of the liquid and the glass, there is another refraction. As this glass medium is denser than the liquid, the refracted light will get bent towards the normal. This is the normal, this is also normal, this is also normal, this is also normal to the interface of the two medium. So here this angle becomes less than this angle as this medium is denser than this medium. And air is rarer than glass, so this angle will be greater than this angle of incidence. So the angle of refraction will be more than the angle of incidence. Here again, as the light is traveling from air medium to glass medium, angle of incidence will be more than angle of refraction. Again here, the angle of incidence will be lesser than the angle of refraction, as this liquid has lesser refractive index than the glass, or the liquid is rarer than the glass medium. So normally these two will be parallel to each other. So there is only a shift in the position, but the direction remains same. So this is parallel to this and there is a shift in this direction. So it was supposed to go like this, now it is going this way. Now if we use the Wollaston's air film, The situation is like this. We have the experimental liquid here, then we have glass boundary, and then we have the trapped air film here. So for our experiment, the experimental liquid can be water or salted water or white kerosene, etc. So it should be transparent liquid. Then only the refractive index can be measured. Now if the light be incident at this point, these dotted lines are the normal to the interface. If the angle of incidence is theta and angle of refraction PR, then at this point there will be another refraction to the air film. As this air film has the lesser density than glass, so the angle of refraction will be more than the angle of incidence, which is again R over here. Now, if theta is such that this R becomes critical angle, then the total internal reflection will start to occur. So the angle of refraction will be 90 degree. And the light will get stopped. So it won't be able to come out this way, like this. That angle we have to determine, and from that angle we can calculate the refractive index of the given liquid. So if this theta does not make the angle of incidence critical, then the light will pass through. And if this theta makes the angle of incidence at this point, that is R becomes critical angle, then no light will come out this way, and measuring that theta we can calculate the refractive index of the given liquid. Now I am going to derive the working formula of this experiment. So at this point, this is the interface of liquid and glass. So angle of incidence is theta and angle of refraction is R. Therefore L mu G. So refractive index of glass with respect to liquid. So liquid to glass is sin theta upon sin R according to Snell's law. And at this point there is another refraction. So refractive index of air with respect to glass. So glass to air, this refractive index sin R C, as at critical angle we call the R as RC, and then the angle of refraction is 90 degree. Therefore sin RC by sin 90 degree is equal to sin RC. And now refractive index goes like this from definition L mu G. So refractive index of glass with respect to liquid can be written like air to glass and air to liquid. So refractive index of glass with respect to air, refractive index of liquid with respect to air. That is the absolute refractive index of glass, divided by absolute refractive index of liquid. Therefore, what do we want to measure here? We want to measure the refractive index of the liquid. So this is the absolute refractive index of the liquid. That means A mu L we have to determine. So from this relation, A mu L can be written as A mu G upon L mu G. And A mu G is inverse of G mu A. Therefore, A mu G is equal to 1 by sin RC, and L mu G we have already determined. So L mu G is equal to sin theta by sin RC at critical angle. Therefore, this A mu L becomes equal to 1 by sin theta, or A mu L is equal to cosec theta. So this is our working formula for this measurement of refractive index of a liquid L with respect to air, or absolute refractive index of the liquid when we measure the refractive index by total internal reflection using Wollaston's air film method. So this angle is this angle where the disappearance of light when seen from this direction occur. So we have to find out that value of the theta for which the light seen from this direction disappears. And now I come to the experimental arrangement of the entire experiment. So this is the schematic of the full setup of our experiment. We normally use a sodium vapor lamp as a source of light, and then we use a standard spectrometer. So spectrometer, we have the collimator here, we have the telescope here, we have prism table here, and the spectrometer has two verniers, V1 and V2. And then we need a container to take the liquid for which we want to measure the value of the refractive index. So this should be a transparent glass container. So we have to pour the liquid. So liquid we have to fill like this, and then we have to insert this Wollaston's air film. We have to insert over here, and then we have to see the light from this eyepiece of the telescope. What happens is light will come along this direction through the liquid and through the air film. Through the telescope it will come and reach the eye of the observer. And what we see here basically is the image of the slit over here. That means the slit of the collimator. So we have to observe here, and we see the image of the slit when the light comes like this. Normally in a spectrometer, prism table is normally locked while doing the experiment, and rotating the prism table we do many experiments. For example, we study the angle of prism, we study the refractive index of the medium of the prism, etc. And for that we normally lock the prism table and rotate the prism, etc., putting on top of the prism table, and with the help of these two verniers we take the reading of rotation angle etc. But in this case, we have to unlock the prism table from the rest of the spectrometer. So what we have to do is, we have to unlock the prism table, and then this air film we have to attach with the spectrometer. Now we have to keep watching the image of this slit through the telescope like this, and initially we have to measure the reading of V1 and V2 when this air film is kept perpendicular to the line joining collimator and telescope. So this air film should be held perpendicular to the direction of telescope, collimator, this line, and it should be held perpendicular to the prism table. And now we have to rotate the air film. Now we have to rotate the air film. As we have attached the air film with the spectrometer, then rotating the spectrometer, we can rotate the air film. And with the rotation of the spectrometer, the reading of vernier V1 and V2 changes. The change of V1 and V2 will give the value of rotation theta, that is essential to calculate the refractive index of the liquid. So we have to rotate the air film this way. So this was the initial direction, and now we are rotating this way clockwise once and then anti-clockwise once. And we have to rotate this air film till we see the image of this slit when seen through the telescope disappears. So we have to rotate the air film and keep on watching through the telescope at the image of slit of the collimator, and we have to find out at what angle theta the image disappears. So that is the value we have to find out from the reading of the two verniers V1 and V2. So initially we have to take the value of V1 and V2 when this is kept perpendicular to the line joining telescope, collimator and the lamp. Then we have to keep on rotating the air cell clockwise first, and we have to keep on rotating till the image of the slit of the collimator vanishes, and then we have to take another reading of V1 and V2. We have to take the difference of the two reading, then we will find this theta, and you have to repeat the experiment identically, only rotating the air film anti-clockwise like this. So measuring plus theta and minus theta, so we will initially have 2 theta, and then dividing by 2 we will have theta. So measuring this theta, we can calculate the refractive index of the liquid with the help of this working formula, A mu L is equal to cosec theta. So now let's do the experiment. So this is my experimental setup. I have the sodium vapor lamp and its power supply here. Then I have a spectrometer, this is the collimator, prism table, then the telescope. And now the source is on, the slit of the collimator is adjusted, and looking through the telescope I am able to see the image of the slit of the collimator. The vertical crosswire of the eyepiece is made coincident with the image of the slit of the collimator. Now this is my Wollaston's air film. I have two glass plates and the air is trapped inside, and the glass plates are joined with the help of glue, and the entire air film is having a metal boundary to make it tight, and this metal boundary is used to mount the air film in the spectrometer with the help of this stick. And to mount the air film we have a special arrangement in the spectrometer. So this arrangement is made so we can fix the air film like this and make it tight. So this air film can be rotated with the help of this spectrometer, and we can make the prism table free. So prism table won't rotate, but the air film will rotate this way. And we have the verniers V1 and V2 here to take the reading to measure the angle of rotation of the air film. Now, as I said, I need a container to pour the liquid for the measurement of the refractive index. So this is a glass container having these surfaces parallel, and this is made of glass. So I have the container, and then if I look through the container again, so the image of the slit of the collimator is visible again at the same position. There is no shift of the image of the slit of the collimator. Now I have to make sure these surfaces are made perpendicular to this axis. So now this is perpendicular. Now I have to pour the liquid for the experiment, that is the experimental liquid, refractive index of which is to be determined with the help of this Wollaston's air film method. Now again, if I look through the telescope, we find the position of the image of the slit remain unchanged. So light is coming from the source through the collimator, it is entering the liquid and then again coming out of the container, so there is no deviation in the path of the light. And at this position we have to introduce the air film like this. Again, you have to make sure that the surface of the air film should be perpendicular to this axis. One more point is, the bottom of the air film should not touch the base of the container. So it should be free. So there should be a gap between the air film and the bottom, such that when the air film is rotated, the rotation should be free. Now again, if we look through the telescope, the image of the slit of the collimator is visible at the same point. And at this point, we have to take the reading of the vernier V1 and V2. So this is our initial reading, V1 and V2, when the rotation angle of the air film is 0. Now we have to rotate the air film about the vertical axis around this direction. Once first clockwise direction and then anti-clockwise direction. And at that time the container should not rotate. So the prism table should be free from the scale of the spectrometer. So you have to make sure that it is free. It is free now, and I have to rotate it. Rotate the air film and keep on watching through the telescope what is happening to the image of the slit of the collimator. So first I am rotating the air film clockwise direction. So it's rotating. Image is still there. Image is visible. Image is visible. Image is visible. Image is off. So we have reached the critical angle. Thus, there is no light passing out of the liquid and we are unable to see the image of the slit of the collimator. So at this point, we have to take the reading of the vernier V1 and V2 again. So once we take the reading of V1 and V2, then we have to come back to our original position. So then I am coming back to my original position. So all the time we have to make sure that container is not rotating. That means prism table is free from the scale. Okay, so we are back to the earlier position. Now I have to repeat the same experiment, just rotating the air film in the anti-clockwise direction. Now I am rotating in the anti-clockwise direction and looking at the image of the slit. So now I am rotating. There is no change. There is no change in the image of the slit of the collimator. There is no change. No change. No change. No change. It's disappeared now. So we have reached the critical angle and we don't have light. So light is getting blocked here. So no light is passing through the air film and we are unable to see the image of the slit of the collimator. We have rotated clockwise once and anti-clockwise once, plus theta and minus theta. Now if we take the reading of the vernier V1 and V2 once again and take the difference of the two readings, then we will have 2 theta, and from that we can find the theta value, and putting that theta value into the working formula I showed in the whiteboard, we can find out the refractive index of the liquid. So this is the experiment, and this liquid I have taken water. We can take the white kerosene, we can take the salted water, sugar water, etc. Whatever liquid we take here, no problem, it should be transparent one, such that it should be able to pass the light. So I have demonstrated here. Let's get back to the whiteboard once again. So I have given you the demonstration how to determine the refractive index of a liquid by total internal reflection using Wollaston's air film. And the reading table for our experiment is the following. We have two verniers V1 and V2, and the rotation of the air film can be clockwise and anti-clockwise. In both cases, we have to measure the main scale reading, vernier scale reading, total reading, and then for a given vernier, we have to take the difference of the two readings for clockwise and anti-clockwise rotation, and that two different readings, the difference of the two readings will give the 2 theta value. So that 2 theta we can get, and from that we can get the theta value. And with the help of this theta value, we can measure the refractive index of the liquid with the help of this working formula AMUL is equal to cosec theta. So the entire experiment is done at the room temperature. So that room temperature we have to note, and as I said earlier, this experiment can be done for water, salted water, sugar solution, white kerosene, etc. So I hope you all will be able to perform the experiment in the laboratory, and the students will be very happy. Thank you for watching this video. Have a nice day.